You ever see an AI do something incredible, like identify a cat in a picture or, write a poem, and you just wonder, how? How does it go from getting everything wrong to getting it right? Well, it might feel like magic, but it's not. It's actually a really beautiful logical process called backpropagation. So yeah, let's get into it and see how machines really learn.
So it all comes down to this one question. Imagine a neural network with millions, sometimes billions of these tiny little adjustable knobs. We call them weights. When that network makes a mistake, how on earth does it know which of those millions of knobs to turn and which way to turn them to get a better answer next time?
Well, the answer isn't some flash of inspiration from the machine. It's actually a super clever and, most importantly, systematic algorithm. Think of it like a highly organized, highly efficient way of learning from your mistakes, just repeated millions and millions of times. And with every single pass, it gets just a tiny bit better. You can really think of the whole process as a simple two-step dance. First, the network moves forward and makes a guess. Then, it looks at how wrong it was and sends that information backward to make corrections. This whole forward and backward flow, that is the absolute heart of how these things learn.
Okay, so let's break that little dance down into 4 clear steps. Step 1, the network makes a guess. Step 2, it measures the error. How far off was that guess? Step 3, and this is the really crucial part, it traces the blame for that error all the way back through the network. And finally, step 4, it adjusts all its internal knobs, the weights, based on exactly how much blame each one got. Now, what's so cool about this is the contrast between these two phases. The forward pass, that's all about making a prediction, right? Information goes in one end, and an answer, this y-hat, comes out the other. But the backward pass is the complete opposite. It starts with the final screw-up, the error, and it sends a blame signal backward to figure out exactly which connections were most responsible for that mistake.
So let's follow that journey of blame. How does the network actually figure out who's responsible? It's definitely not random. Backpropagation uses calculus, specifically something called the chain rule, to precisely calculate how much every single weight contributed to that final error. It's basically a mathematical way of distributing responsibility fairly. Okay, so the amount any single knob gets adjusted really comes down to 3 things. First, the size of the overall error. Makes sense, right? If the network was way off, the adjustments are going to be big. Second, the path that blame signal takes on its way home. Every connection it passes through can either pump up or tone down the signal, which changes the final adjustment. And third, the input value that went into that specific weight. I mean, changing a weight is going to have a much bigger impact if the signal passing through it was strong in the first place. Now, this all sounds great in theory. And it is, but for a long time, researchers hit this massive, massive wall. They'd build these really deep networks, but after a certain point, they would just stop learning. The blame signal was literally getting lost on its way back. And the problem started with the individual neurons. See, the early activation functions they used were shaped like an S. So if a neuron got a really high or a really low input, it would end up on the flat part of that S curve. And at that point, it becomes saturated. It doesn't matter how you tweak its input anymore, its output barely changes. It basically goes deaf to the error signal. And this quote just nails the mathematical problem. As the pioneers of this stuff pointed out way back in '86, on those flat parts, the derivative, which is really just a measure of change, is almost 0. And since the blame signal is calculated by multiplying by this derivative, well, you're essentially multiplying your error by 0. The signal just dies right there. So when you have many, many layers of these deaf neurons, you get this huge network-wide problem called vanishing gradients. That blame signal, the gradient, has to travel backward through all these layers. And at each step, it's getting multiplied by a tiny number. After, say, a dozen layers, you're multiplying something by 0.1, then by 0.2, then by 0.05, and the final signal is just practically nothing. It vanishes. So what happens then? What's the big deal when that crucial blame signal fades from a shout all the way down to a whisper by the time it gets to the first few layers of the network? Well, those early layers, the ones that are supposed to be learning the most fundamental, important features, they just stop getting updated. They stop learning, period. This was a huge problem. It threatened to stop deep learning dead in its tracks. But the solution wasn't some crazy new math. It was actually better, simpler engineering. Researchers realized they didn't have to fix the algorithm, they just had to fix the signal itself. And I mean, just look at the difference here. It's night and day. On the left, you've got those old S-shaped functions with their flat ends that just killed the gradient. And on the right, you have the modern solution, ReLU. It's so simple it's almost funny. If the input is negative, the output is 0. If it's positive, the output is just the input. The derivative is a constant 1. This means the blame signal passes through completely unchanged. It's a beautifully simple, elegant fix.
But fixing the signal was really just the first step. Researchers also came up with a whole toolkit of smarter ways to use that signal more effectively, helping the network learn way faster and more reliably.
So instead of just taking one tiny little step in the direction of the blame signal, that's basic gradient descent, we now have these things called optimizers. And you can think of them as these really sophisticated navigators for the learning process. They use that blame signal in much, much smarter ways.
And there are some great analogies to help understand them. Momentum, for example, is like a heavy ball rolling downhill. It builds up speed, which lets it just blast right past any small bumps or shallow valleys in its path. And then you have Atom, which is one of the most popular optimizers today. It's like a smart ball that not only has momentum, but can also adapt its speed, taking bigger steps on the steep slopes and smaller, more careful steps when the ground is flat.
Now, it's not always about signals vanishing. Sometimes you get the exact opposite problem, exploding gradients. This is what happens when the blame signal gets multiplied by really big numbers over and over, growing exponentially until it's just enormous. This makes the weight updates so huge that the model becomes totally unstable.
And once again, the solution is just elegantly simple. It's called gradient clipping, and it's a super basic rule. If the blame signal gets bigger than a certain number, if it starts shouting too loud, you just cap it. You literally just turn down the volume, and that stops the model from flying completely off the rails. Okay, so we've been through the guesses, the errors, the signals vanishing, and the clever fixes. What's the big picture here? What is the main takeaway from all this?
It's this. Backpropagation completely demystifies machine learning. It's not some unknowable magic black box. It's a beautiful, powerful, and honestly, a surprisingly logical feedback loop. It's a system for assigning credit, assigning blame, and allowing a massively complex network to fine-tune itself through millions and millions of tiny, targeted corrections.
And that really leaves us with a final thought, doesn't it? This elegant process of error correction, this is the engine that's driving this entire AI revolution. So if a machine has a way to learn from its mistakes this systematically, what does that say about the future? What is the true limit on what we can actually teach it to do?